Yeah, Joel's up first.
And take it away, Joel. It's all yours.
Okay, so I presented this slide last time, well, in December. I'm just gonna present on some of our updates since then, and maybe try to add some context around Tom's demonstration last week of the NeuroGlancer viewer. So we're trying to use the NeuroGlancer viewer as our front end for these tools, our alignment tool and the reconstruct tool. And this is sort of the pipeline that we're trying to build. Starting with a raw stack of TIFF images from your EM microscope. We want to put those into a ZAR container format, which I talked for some time about previously.
Can I interrupt you 1 second, Joel?
Yes, please do.
Does it have to be a TIFF format? It can be any format, right? A picture?
Well, it could be, yeah, we'd have to write the code for that. Right now, it would have to be TIFF, but I mean that it'd be simple to, extend the,
Because a lot of our images are either BMP or JPEG from old data sets, for example.
yeah, so we'd be able to do that.
Okay,
Yeah.
great. Thank
Yeah,
you.
the data inside the ZAR is just grayscale values in arrays.
Yeah. So no matter what image format, at the end of the day, like Tom said, it's just values. And if you can just strip all of the header off the image files, I mean, what you're left with, no matter what the image format is, unless it's like a proprietary weird format and they've got it all locked up and try to make it so you can only use it with their software and such, those formats might be a little bit more difficult. But for the common file formats, there shouldn't be any problem with extending the ability for to be able to put those into ZAR. Okay.
What did you say, Art?
Avoid DICOM. It is super complicated. So, but we don't need it for this.
Right.
Okay. So once we have them in the ZAR, and we're not 100% right now certain if we're going to put them into the ZAR before or after the alignment. Whichever way it happens, it's going to have to happen fast, because when the user, we don't want the user to wait. And then we don't want them to wait because they're already waiting for the alignment. That's the algorithm that's run. And if they're waiting for that, we don't want them to wait too long for to put it into the ZAR format. So we've been working on parallelizing that so that we can do that, in a multi-process way where we can divide that up to workers and threads and use the infrastructure attack eventually when our application is running there. We'll want to be able to make the most use of the cores and have an application that when it's running, it's CPU bound. So Tom mentioned last week, I caught up on the recording, that we weren't fully parallelized yet, and so that was true. We're now fully parallel. So previously, only the image scaling, and I see that Arlo's here, who used to work at Janelia. His colleagues at Janelia have some scripts that do the scaling in a very, very, what I found to be a very flexible way. So producing the scale hierarchy. And so we've been using that code. That is parallel already. So that part has always been parallel. What wasn't parallel and where the bottleneck was copying the images into the ZAR. So that part, we have also made that parallel now. And so I was hoping to maybe demonstrate that today. And so what I'll do is I'm logged in right here to one of our compute machines, and I'm just going to start it right now. And by the time I'm done talking, it should be into the ZAR. So I'm going to point my script here at a stack of TIFF images. It's a very large data set. So this is 103 gigabytes. And when it's done, it will be in the czar, it will be scaled, and it will be neuroglancer ready. So yeah, and so this all goes to sort of the data, sort of the data pipeline, because we've already got the alignment code, and so now we're kind of reaching the end of having this all kind of figured out with the data pipeline, how the data is going to be formatted, how we're going to get it into the format, how it's going to be fast, and then how it's going to be compatible with the neuroglancer viewer. And then so after I demonstrate this, then I'll maybe pull up the neuroglancer viewer. Maybe I'll just let Tom do it because he's got the big data set. That doesn't
Yeah,
fit the laptop.
and Joel, last night I
Yeah.
copied over your new version of this,
Cool.
the one that you're about to make again. I have it on my laptop here, so I'll be able to demonstrate that.
Cool. So I'll just so I'm gonna run the make Sark script, and I'm gonna run it on this data set right here. It's the name of the directory. So this directory just has 269 TIFF images in it, very big ones. And then I can set the chunk size to be okay. So what I'm going to do here is I'm setting the chunk size. So when this gets chunked, we want to optimize the chunk shape, and that's something we've also made a lot of progress with. So the way we're doing it now is you got a stack of TIFF images. So there's 3 dimensions here. You've got the length and the width of the image, and then you've got the height of the stack, or the number of images. And so the way to chunk this that makes the most sense, we've found, is to use chunk sizes. So neuroglancer recommend that the neuroglancer developers recommend a 64 by 64 by 64 chunk size, but I think that's just sort of a generic approximation, and for something that they can just kind of say to users that will work with any data type. So we're working with images. So what we do is our chunks are in the 3 dimensions. For the Z dimension, just 1. So if the images are small enough, we could just use the length and the width of the image. So 1 by length by width of image. But these images are really large, so I'm going to use a chunk size that's a multiple in the length and width. And so I already know what that is. So the full size of these images is 24,576 pixels. So 1,536 is, I think it's a 16 times multiple of that. So that's going to be my chunk shape. Okay. And then we can compress it or not. We don't have to compress it, but we will for just because, and it helps with the, I'm not certain. I think it actually helps with the rendering when it's compressed. Don't quote me on that.
And it's a lossless compression.
Lossless compression, good to emphasize that. So, okay, so next parameter I'm gonna put in is that. So the CNAME, and that's gonna be, we're gonna use Z standard, which is the fastest we found. And then the defaults are mostly good here. Okay, so, and then I can also set workers and threads. And I'll show you that guys in a sec. I'll show you guys that in a second. I'm just gonna keep this running for now in the background. So this will start. And this shouldn't take so long.
It says unrecognized argument.
Oh, 2 dashes.
ZSTD.
Z standard, it's the compression library that is fastest we have found. It's the fastest. Okay, so this will be running. So the parallelization for the copying it into the czar uses Dask, which is a very popular Python library for multiprocessing. And it basically re-implements a lot of the NumPy, which I'm sure many of you are familiar with. The NumPy library sort of re-implements a lot of those functions in a way that's parallel, like already. Or you can create your own task graphs if you wanted to. But the task graphs for this are, oh yeah, okay. So that's what I'll show too. Is
So I have a quick question, which is, what does ZAR stand for? The only thing that comes to my mind is bizarre.
I believe it stands for Z array.
Z array, okay. So like the Z stack.
I believe so.
But technically it can be n-dimensional. So why it's called Z array might have some other context.
Oh, we have X-rays, so why not Z rays?
Right.
Also alpha rays, beta rays, gamma rays.
Omicron rays.
There you go.
So this
Yeah.
is the task graph for the computation that's running right now. So this is a feature of Dask where it will print out the Dask graph into an image format like this, which is kind of nice. So you can see the task graph is pretty simple. And this, it's just, you can imagine certain programs that are trying to do a lot of things at the same time, but those things are different things. And so the task graph starts to get really complicated. So you've got this thing that needs to finish before another part of the code can run. And then you've got multiple other things doing other things, and sort of they're all linked. The different parts of the code are all linked in weird ways. And so we don't have to worry about that here because of the chunking. So the chunking, when our data is chunked, and one of the benefits of the chunking is that it makes parallelization very straightforward. So all we've got is just a bunch of different threads that are, you can't work on one chunk at the same, two workers can't work on the same chunk, but you have many chunks and you can work on many different, depending on the number of cores is going to be your limiting factor there. Depending on the number of cores you have, you can be working on many chunks at the same time. So we got all of these chunks and it's going to write to all of these chunks. And this is the task graph for the scale 0. So we're just writing the image and doing it. And so that's why there's going to be about, if you look at the numbers here, there's going to be about, for the data set I was working with here, there's about this many, about 100 and something images. And so you can just work on all of those at once. So I just wanted to show an example of the task graph. Okay, so this is going to keep running. Let me get this out of the way. There we go. All right, so last time we met and I was here, we didn't have it, so it works with this. We didn't have the code for the scale hierarchy totally implemented, which, as I said, is the Genelia code, which for now we're going to stick with. Right. So another thing that I thought would be interesting to you guys is to just show you what one of these ZAR containers looks like. So if you just open it up in like Finder, so you've got multiple directories here. This is the scaling. So this is the scale 0 image, and then scale 1 and scale 2. And so if you look at the number of files down here, so in the scale 1 image, you have over 12,000 files. Then in the scale 2 image, you still have over 12,000 files. In the scale 3 image, you got 3,000 files. And then in the then in the scale 4 image, you have less than 1,000 files. So why is that? So we're scaling down, but our chunk size is staying the same. So if you're trying to represent less data with the same chunk size, then you're going to get fewer files, and these files are the chunks. We don't have to worry too much about these chunks. Art might, if we do go the route where we want to have the container in this, sorry, we want to have the data in the container prior to alignment, then in that case, Art will have to, in C, reconstruct the images from these chunks. But it's not really, it doesn't really matter. It'd be kind of nice if we had them pre-aligned, because then they don't have to be aligned twice, like in Art's, because Art aligns them also. It'd be nice if they're aligned ahead of time. It doesn't really matter as long as we can do this quickly, and the amount of time we've been saying we would like to be able to do it in. We've sort of been jokingly saying if you could do it within the time it takes to get a copy. And so the user would click a button to align, and then
And you don't want to have to fly all the way to Costa Rica to get that copy.
Right.
I'm aiming for the time that it takes to take a sip of coffee.
Yeah, that would be nice.
okay. So since last time, we've got the code implemented to do the multi-scaled pyramid. C standard, that's the fastest compression we found. Parallelization, chunk shape, we're now using the chunk shape that I described, where as I described, where the Z dimension of the chunk is just 1. So it's just, it pertains to one image. So how we were doing it before is where the Z dimension of the chunk was the length of the image stack. So basically you can imagine like columns through the Z stack. And that, I guess, made sense to me at the time, but after researching and playing around and testing, I think that it makes more sense to do chunks, where the chunks are where the Z dimension is one in the X and Y dimensions of the image. Or
Well, it really depends on what you're doing, as far as if you're working section at a time, then this is the right choice for sure. If, on the other hand, you're doing a lot of three-dimensional browsing and out-of-plane viewing, then that would be different.
Yeah, well, I was just going to ask what benchmarks you've run on the compression algorithms, because what we found was that BLOS compression worked the best. But if you've actually run those tests on your data and you found that that works the best, then ignore that. But we found that BLOS renders significantly faster in the browser.
Sorry, what does?
BLOSK, BLOSC.
Okay. So we are using BLOS. This uses BLOS.
Okay, cool. Yeah.
So the thing with BLOSK though, or one thing with BLOSK is, so we're using Dask here, and when you use BLOSK, you can't. So BLOSK tries to be multi-threaded, and so if BLOSK is trying to be multi-threaded, you can't have Dask be multi-threaded also, or it'll wreak havoc. So I have to manually turn off you can set BLOSK to not try to be multi-threaded, basically. So am I speaking with Arlo here?
Yeah.
Okay. So you guys found, can you say that again one more time?
Yeah, for visualizing large data in NeuroGlancer, regardless of whether you have a scale pyramid or not, we've found that BLOS compression in your ZAR container speeds up compared to gzip and other.
Well, BLOS isn't a particular compression algorithm. You can set the algorithm, so you can do Z standard with BLOS, and you can also do like zlib with BLOS, and I've got the list, I think.
Okay, I'm just talking about in terms of like when you actually like create a ZAR data set, right? You can define, like when you do create data set, you can define a compressor, right? Mm-hmm. And in terms of compressor, the ID, if you use ID, BLOSK, and C level 5, this results in pretty fast viewing.
I've been using C level 1 because it compresses faster.
Okay.
I'm not sure how that affects the rendering, but in my experience, it doesn't really matter because the rendering is so fast no matter what. So we're more concerned with, from a practical standpoint, the user not waiting forever. So we're trying to eke out as much performance as we can. And one way that to gain performance is to A, use Z standard, and B, use a low compression level or no compression at all. Because the less compression, you keep getting marginal gains as you compress it less up until not compressing it at all.
I mean, I guess it depends on the size of your data sets that you want to be able to load in there, right? If it's not that big, then I guess less compression is fine.
So yeah, our plan is to use this with the TAC infrastructure. That's our number one sort of objective or purpose for this technology. So we will have. I don't think space is a concern, so we're not worried about space.
Also, the data sets we've been working with here are on the order of 150 gigabytes, or the size of the whole data set.
So Joel or Arlo, Z standard allows you to import a prior context that improves the probabilities and therefore the compression. Have any of you seen if that's possible with ZAR?
I haven't done any tests with that, no.
Sorry, what was the question?
For other reasons, I'm very interested in that for data that we have here at PSC.
Sorry, could you ask that question one more time?
So compression schemes sort of learn in a way the probabilities that you're dealing with. And so when the Z standard compresses each chunk here individually, it has to reacquire those probabilities anew. Whereas in a given data set, the probabilities are, they're scattered, but they're not wildly scattered. So giving prior information that's along the right lines in terms of probabilities that enable the compression gives you a higher compression ratio and saves time as well.
I see but that's part of the algorithm that's built into it, right? Like as it starts compressing, it starts learning.
Yeah, but somehow you have to provide this extra information. And although I'm very interested, I haven't gotten into investigating it very thoroughly, and I just wanted to see if anybody else had looked at that.
Would be interesting if we can provide that to this, because a lot of the data we're working with here is very similar. Would probably be pretty similar in those probabilities, I think.
Yeah, absolutely. And especially if you have areas that go out of bounds, so to speak, out of tissue, those should compress to practically nothing.
Right.
And yes, it will learn that individually, but it would be nice to have some way to specify that.
But the data that is going to be running through this program is going to be different, and maybe of even different image formats,
Oh, absolutely. Well, so what I'm thinking is that somewhere here you would have at the top of the tree some information about that. And I don't know yet whether ZAR allows that or not. But in some other things that we're doing here at PSC where storage efficiency is more critical for these really, really huge data sets, we're interested in getting nearly as much compression as we can.
Okay. Yeah, that's something to look into. We could kind of pre-train it.
Yeah.
Okay.
And it won't be perfect, but it's just an improvement.
So previously, as I said, we were using a NumPy array. Now we're using a Dask array. Dask arrays are great. And then I wanted to show you guys what the metadata files look like. There has been some discussion. Kristen, I think you mentioned wanting to have experimental details potentially in the metadata. So the place that would go would be right here in this .z attributes file. So with our
And it looks like these Z attributes are exactly JSON, right?
Yeah, this is JSON.
Yeah.
So each one of these folders that has the scales is going to have both of these files within it. .z attributes. So this is actually NeuroGlancer specific right here, because this is where you can put application level data. Application level data, metadata, and you can write code that can do stuff with this. So or not. So that's why we could have information about the experiment. You know, I imagine as somebody goes to align their images, they're asked that they're prompted to input some information about the experiment and what have you. So.
And then there's one more .z file, one level up.
Yeah,
That is pretty trivial.
there's
I think.
.z group, which is pretty trivial. Yeah.
Joel, yeah, I think it would be nice to have that. Sorry, my taskbar was hiding my ability to unmute myself. A moment to undo my taskbar. Yeah, I think it would be great. And this really sounds like you've made huge progress in thinking about how to go about doing this. I meant to respond, but like I said, it took me that long to figure out how to uncover my taskbar.
And I wonder, maybe Arlo knows something about this. So for alignEM-SWiFT, we have a JSON format that we've defined. And right now that's stored as a separate file. And the question would be whether or not we should put the JSON for that inside the Z attributes, or would it be side by side as a separate file, but within the ZAR container?
Yeah, I mean, you could do either one, right? I mean, it's kind of up to you. I mean, it might get kind of messy if you have it as its own kind of, nested dictionary inside the JSON. Maybe it's easier to just have another hidden file. The main thing is that the Z attributes file just has offset and resolution. Those are the two things that NeuroGlancer for sure cares about.
Yeah. Okay. So I think maybe my preference then would be we'll make a separate file, probably at the top level of the ZAR, for the alignEM-SWiFT JSON project file.
Yeah, ZAR is a pretty smart format. I don't think it cares too much if you want to add your own hidden files.
Yeah,
So,
the reason I say that is because it looks like this .z array and .z attributes in there doesn't have a top level key for the dictionary.
So you can also
yeah.
Sorry.
I was just going to say, since it doesn't have a top level key for the dictionary, it looks like this stuff is all kind of really ZAR specific, except for maybe the .z attributes, right? But
so this stuff is data set specific, but there's a level above inside the actual ZAR. There's a Z group. So you could actually put it inside the Z group or right next to the Z group. If it applies to multiple data sets in one ZAR file, then you should put it in that level. But if it applies to a single data set. Okay.
Yeah, and it does, right? It applies to the entire ZAR.
Yeah.
Everything in the ZAR is what it applies to. So yeah, that would be good. That's a good idea. Okay, thanks for the.
Is there a place for sort of free-form comments?
Yeah, that could go in the Z attributes.
Okay. One more question while we're sitting here, related to the compression again. I know there's some option in addition to the compression Z standard or whatever, for a filter that you can insert. And again, I haven't investigated enough to know how to do that. But in other things, so Z standard or gzip or whatever, just takes the stream of bytes and is using the probabilities and co-occurrences and so on. But it's not taking advantage of the dimensionality, 1D, 2D, or 3D correlations that all images have. So putting in a filter that does differencing along the dimensions, and we can talk about this in our Tuesday meeting sometime, makes a substantial difference.
Yeah. And this is what MPEG is all about.
Yeah.
Right.
Yeah. So compressing differences is much better than compressing the values themselves.
Yeah. And if you know that there's correlations, say in MPEG across time, right?
Yeah.
Then you do even better.
Right.
Right.
Yeah. A fourth dimension.
All right. So this finished. It actually finished a few minutes ago, and we've got our final result. We've got our ZAR, and so that's NeuroGlancer ready now. And the time that took was 500 seconds to make the czar and 600 seconds to make the multi-scales.
That's a 10-minute coffee sip.
Yeah. So
That's a long draw. That's more like,
Yeah.
shot, maybe.
Well, you could
It
walk
depends on
out
the
to the,
size of the data you're working with.
yeah, you could walk out to the coffee cart at Salk and get your coffee and come
get
back.
How
Wouldn't
many?
You wouldn't have to fly all the way to Costa Rica.
How many
Right.
workers did you use, Joe? How many
okay,
workers?
so I was going to mention that. So let me also run this locally, so I can set the number of workers and the number of threads and stuff. But the problem here is I'm not optimized for cores, and it has something to do with the configuration of this Debian 9 compute machine, and it's not for some reason it's not working with Dask.
So that wasn't using nodes at tap.
So
right?
it was using Dask. If you don't tell Dask how many workers, then it will try to do it automatically. And I don't think it's knowing what to do. I think it's very confused. So let me run this.
But this was running on a machine at Salk
Yeah,
that has 24
that is
cores.
48 cores.
Well, it has 24 cores.
But more importantly to me,
48
the
with
data
hyper-
is sitting on NVMe.
It's 24. It's 24, Joel.
Gotcha.
48 is a lie. That's why it's getting confused.
Yeah. The fact though that the data is sitting on VME is the bigger difference.
Oh,
So I don't know if you had any percentages here of IO wait time versus CPU time, but that will vary widely as you go from NVMe storage to just standard disk storage.
I see. Now, while you're working on this, I have one more question. So you're not envisioning putting trace or any other kind of analytical files in the same ZAR package, right? The ZAR package will be basically the image and metadata, and then you'll work with it to create other kinds of data. Is that the idea?
Well, this is something to discuss with Edwin in the design of Reconstruct Plus, and whether or not the ZAR. So I think in discussions we've had with Arlo in the past, ZAR can certainly have multiple kinds of data coexisting. So there could be data in the ZAR that represents the traced contours.
Or can it be like a cat-made instance, or not instance, but I mean, as far as I'm concerned, Tom, just in terms of thinking about the design, it would seem to me that there's value in separating image and metadata from analyses of that image, simply from the point of view of how big are these files? Because like in my course, for example, we have one set of image files that Reconstruct, when you open it, you can just say find it, and it goes and finds the images. You don't have to have the images in the same subdirectory. So there can be one set of images that 40 students can find and do things in. Independent of each other. And so there's something to be said for keeping analysis, I think, separate from the images themselves. But it's useful to have the metadata, which is a small amount of data, usually. Well, it could be big, but at least how to find the experimental data.
Well, certainly it seems to me that it seems to me that part of this problem has been solved already by the folks at Genelia and elsewhere, because we see these example data sets that carry along a lot of this other information. But I don't know if that's NeuroGlancer itself or all embedded within the ZAR format, or whether there's other external files. So
while you guys are talking, I just want to explain what I'm going to be showing on the screen.
Yes, please go ahead. We were just doing a sidebar while you're getting set up. You're in charge, Joel. Take it back.
People to know what they're looking at. So now I'm just working on my computer here. And this is this is the volume Joseph data set. It's about 4 gigabytes, smaller, manageable, something that I can test code on here on my laptop. And I'm running this with one worker just to show you how slow it can be. And this is only going to use one core. This is only using one core. And then when you go to workers, you see that there's only one worker. So that's what you guys were looking at just there. And if I now run this, kill it, and then run this with, this is an 8-core machine. I'm gonna run it with 8 workers and 2 threads per worker. If I run it now, this should finish within like less than 30 seconds. If I refresh this.
Joel, it looks like it finished out on your,
No, it's still
oh,
running.
I see, no, it's running. Mhm.
There we go.
This didn't update, so you missed it. So this is only this workspace here is only for Dask. It's not going to show the so once it started doing the scaling, it's doing the multi-threading using a Genelia library called Daisy. Is that correct, Arlo? You guys wrote the Daisy package?
Yeah,
Yeah.
Daisy. So we wrote Daisy just because we initially tried with Dask, but Dask wasn't scalable to the size of the data sets that we needed to do stuff with. And so, yeah, we wrote Daisy. And the couple nice things about Daisy is that, well, actually, one of the downsides of Daisy is that you can't just like have like a function that doesn't like do anything, like that doesn't write data out. Like in Daisy, you're assuming that you're preparing a data set and writing it out. And we designed that because it was very specific to our needs. We're always reading and writing data to like ZARs or N5s. One of the nice things about Daisy is that you can also do, you can parallelize graph edit operations using like Mongo databases, like collections of nodes and edges and whatnot. So, but yeah, that's what the scale pyramid, I'm assuming you're using scale pyramid and the FunkyLab GitHub. That's, yeah, that's the scale pyramid that we wrote for using Daisy.
I'm not sure why this workspace is starting out, but just take my word for it. Basically, when I increase the number of workers, it totally maxes out my CPU. Well, I can also do this. Let me pull it back to monitor. So you should see that my cores are all pretty maxed out as this code runs.
They are. Mhm.
So I see you're using volume Joseph. It's amazing how that data set gets around.
Convenient.
Everybody seems to think volume Joseph is the be all to end all. It was. The animal I perfused in 1984, and then Joseph and I spent many years doing the first round of tracing, and Tom and Justin cleaned up those traces, and it's just been it's been the workhorse.
Well, for these tests, of course, it's not a matter of the content so much as just to have an apples to apples comparison basis.
Yeah.
Yeah. And then in the end, because it has the dense reconstruction, we can then take it all the way to the end and use it as ground truth for other segmentation algorithms, et cetera, or meshing algorithms, lots of things you can do with it.
I'm glad we didn't have to do any more ground truthing. Although I remember I do have 2 other data sets that have been fully reconstructed.
Oh,
we don't
you do?
use we don't use volume Joseph in the course because it's so big.
Oh, I see. Okay.
I have a series called Oblique that's only 91 sections and has a cylinder in the center of it. It's much smaller than volume Joseph, but everything in it's been reconstructed too.
Uh-huh.
So we're using it to train students to understand what they're doing. It doesn't look very well aligned.
So Joel, when you just finished your run of compression there on building on your laptop, what storage was there? Was that disk or flash?
This is disk. This is to disk.
To solid state disk or
solid state, yeah.
Yeah. Okay.
Yeah. So I think if you ran the same tests with a old style, spinning disk that's 10x cheaper, then you would no longer max out your CPUs. You would be a lot of IO weight.
Yeah. So this is.
So what are we looking at here, Joel?
Well, this is the volume Joseph data set in ZAR format being read by the NeuroGlancer viewer.
But it's not an aligned series. version of it.
It is aligned. It's already aligned.
Doesn't
So,
look aligned.
I didn't
so
align it here today.
So the reason why it's looking a little jumpy is because Zoom can't keep up with how smooth he can scroll through it.
Okay, because it looks very smooth to me here.
Yeah. So use the dot and comma on the keyboard and go one step at a time. Go.
I see. That's better.
But it's not super aligned.
But
No,
it's- yeah,
not.
this
It
isn't-
doesn't-
it's
it doesn't
aligned
really let it shift.
Yeah, this is aligned the wrong way. It's done with alignEM-SWiFT, but it's done using the wrong method that we still have to improve on in the actual code that we're using, right?
I see.
That's what remains to be done.
Can you blend two adjacent images? That will help us see how good the alignment is. No. Can NeuralGlancer do that?
No,
Arlo?
I don't think so.
You can't
Blend to
adjacent.
adjacent. No, you'd have to write that function.
That's a very useful function.
I mean, it wouldn't be hard to write that,
Mhm.
right? You just have the same layer, right? Offset as a separate layer, and then you have a 0 layer in the middle, and then you just blend them and write it into it. You could do that offline. I think this is really
We
cool.
just did a space bar in Reconstruct, and you can blend it and unblend it, and it's extremely useful for knowing whether or not you're following the right structure or if it's ended.
Yeah, I mean, you could do something like that with callbacks, for example, right? You could just have that function, bind it to a key, so whenever you press it, it executes it. I showed Joel and Tom some examples of that.
Yeah.
You could also have it as a GUI function if you extend the front end.
So here's Arlo's example. So if I press T, it'll return the coordinates of the mouse. Oh, I'm in PyCharm here, so it's going to be fun. Yeah, see the mouse coordinates right there. So that's because I pressed the T button. It's a very simple callback. And so I guess that's actually a good segue to the last thing I want to talk about, which is we're not certain that, so a callback function is going to let us write functionality in Python that can be bound to a button press. And there's little more than that you can do with it. So it doesn't offer much in the way of a user interface that has menuing and accepts user like typed information. You can't do that with callbacks. So how much can you do? And that's maybe the most functional feature possible that only depends on the NeuralGlancer Python API. So when I demonstrated sort of how you can start to configure this with different window panes and stuff, that you can't, the customizability of the NeuralGlancer Python API is very limited. So the alternative course of action is to fork the NeuralGlancer code and start from there. And that gives us a whole lot more sort of power and ability to customize the GUI just the way we want, and to really get something that has all of the same functionality as the existing Qt GUI. So that's probably the last, phase of this process, is to fork the NeuralGlancer code, and all of the work that we've done in like understanding like how NeuralGlancer works is helpful, and it all comes into play. So
I like the name of your program, alignEM-SWiFT.
I think Tom came up with that.
I mean, you're always good at naming stuff. You're muted on purpose because you also have a nasty way of typing right into your microphone. So I asked Anna Marie to mute you whenever you're typing.
Oh, okay. Okay. I said Joel invented that name. I'm pretty sure, Joel, that was your name.
Tom's also modest, Joel, so you can take the credit. Go ahead. He won't beat you up.
That was Tom. That was all Tom.
Well, I don't think so. That's not how I remember
Actually,
it.
if you really want to know, it was me.
Okay.
No, it was me. I'll take credit. I'm the one who noticed it. I get to have credit.
Or are we sharing
Yeah,
credits
I
or
get that.
blames here?
Yeah.